Okay, I always ask this question when I start a group like this. Who has never been here before? How is that possible? We've been here 12 years. It's the story of our life. Anyway, let me tell you a little bit about the observatory and its history and what we're doing here. And then I'll introduce Jason, our speaker for tonight, with a much more interesting topic than what I'll talk about. Anyway, the observatory is run by a non-profit separate from the high school, although it is on high school grounds. Little Thompson Science Foundation runs this observatory as a public facility, a public observatory open to the public any night of the year, any day of the year, by appointment. So you can go to our website, look at the schedule. The website is starkids.org. Make an appointment, find a date that's still open, make an appointment, and we'll put a volunteer in here to help you with the telescope. We're running on donations, so we always have to ask for small donations. There is a donation box at the very back of the room next to the exit. So if you like what we do here, you can leave a little something in the donation box. We have some mugs, and we have a special sale on t-shirts tonight. Cool. Oh, okay, good.
It's very collectible because they only have one dog. We have two dogs. So they're really
And I think we'll give the kids all a t-shirt if we still have small sizes, right?
Yes,
I don't know if we still have small sizes. Any kids that sits up front can get a free t-shirt.
Sweet, that means I got two. Yeah, we'd like to get extra large.
Cool. Sure. Yeah, back a little bit. Okay. It kind of shows that John is in marketing, right? Because he knows how to sell that kind of stuff. Anyway, we started building this observatory in 1997. Then we got a telescope donated from Telescopes in Education in Mount Wilson Observatory in Pasadena, California. In 1999, we finally opened the building to the public after spending about a year and a half building it. And as you noticed, we're not on top of a mountain, right? It's easy to get here. We even have the pleasure of Cleveland next door, right? Total antithesis of observing. But what we do here is not be nerdy astronomers, but we like to get the K through 12 students to not be intimidated, not to be afraid of math, science, physics, basically the difficult stuff in school. And we're using astronomy as the teaching tool to get them kind of as in a game, get them interested in that stuff. So that's what we do. In January, we had our 50,000th visitor come through here, with about 70% K through 12 age group, and the other 30% being adult people. Tonight, unfortunately, the clouds look like are coming in, so somebody didn't think clear skies. I don't know who, right? Anyway, what we'll do is we'll have a nice presentation by Jason. And then if the clouds move away a little bit, we can probably see the planets. Even with some cloudiness, we can still see the planets. It helps when you have an 18-inch eyeball, right? I mean, it's kind of better than having a little one. Anyway, any questions as to what we do or how we do it? We run with a full crew of volunteers. Anybody who wants to volunteer here, just go to the website and sign up. We'll teach you how to run the telescope. We'll teach you how to talk to a crowd like this. And you can go play with the telescope when the groups are gone. So kind of a nice enticement again. We learned that from John, our marketing guy. So let's see, tonight Jason Fettig, a Ball Aerospace mechanical engineer, is our speaker. He got his degree out of Purdue University in Indiana, mechanical engineering, and he did an internship. That's one way for kids to get involved in aerospace. Once you're in school, you can kind of sign up for some internships. and go have some practical experience at aerospace companies or whatever technical company you want to go. And I think you did it for 3 years. And then ultimately he got hired right before the economy tanked, right? So just in time. And Jason is going to talk to us about a project, the NPOS preparatory program, which is kind of a gap filler, weather, earth observing satellite that even I worked on in the early 2000s. I mean, that's been a long time in the making. I didn't know satellites had a gestation period of 12 years or so, right? It's kind of crazy. So Jason will have some slides. He'll have a little model. Question? Nope. Okay. And you can ask questions during the presentation,
Absolutely.
right? Absolutely. So don't be shy. Ask him questions if you don't understand something. If he starts to talk engineering, you may just ask questions. Afterwards, we'll hopefully open up the scope again to look, but I'm not so certain. So if everybody thinks clear thoughts, maybe the clouds will go away.
You know what? Can I make a suggestion?
What?
Because I'm Carol.
You're Carol, yes?
Since so many have not been here, I'm sure they're curious about the Star Wall.
Okay. After the presentation, why don't
Yeah.
we maybe do a little session on the star wall? We can turn the lights out. We have black lights for those of you who grew up in the 60s. We can make it pretty psychedelic here and have some fun. So we can play a little bit with the two star walls. You see one, Lakota Sioux, Native American Indian constellations from the Pine Ridge Reservation, South Dakota. And one, of course, your Greek-Roman standard Western constellations. And we can tell you all kinds of stories about those. For those of you who haven't been up to see the second telescope here, the 24-inch from Mount Wilson in Pasadena, we will do tours after the talk, show you that telescope. It's finally moving, so the next step will be to get the dome moving, and then hopefully we can have that one in operation. I'm not going to go out on a limb, but maybe this summer. Great. Yeah, keep your fingers crossed, your
I'm
toes,
here every
everything.
Saturday until it works. So.
Okay, good. Anyway, if there's no other questions, we'll turn it over to Jason. Turn the lights down a little bit, John. That would be great. Thank you. This thing works? Okay. Thank you.
Hello, everybody. My name is Jason. I work for Ball Aerospace, and we recently launched in October Suomi NPP. And this is a very long program in the making, started back early 2000s. Normally, program doesn't go that long for satellites that we build, but there was a little bit of schedule delays on this one. But it gave me the opportunity to work on it, so I'm okay. So, the delays that we had. The NPP stands for NPOS Preparatory Project, which is a long acronym that just means that we're going to build a bunch of these, but we wanted to test out some of the technologies first. And so that's what this satellite does. But that doesn't mean it's not important, because there's a lot of new technologies that are really cool that's going to help the nation understand our weather patterns better and also long-term climate change. After it launched, they added the Suomi name to it, and Suomi is the last name of a professor at the University of Wisconsin who had a lot to do with early weather observation technology, especially with satellites. He got into this in the late 50s when satellites started becoming very important. So he designed a lot of the instruments that went on satellites that produced the cool TV images that people, that was brand new technology to turn on the news and see clouds moving from satellite pictures, and he had a lot to do with that. So in honor of him, they named this satellite after him. So, the first question is, where do you start when you want to build a satellite? So scientists usually say, we've got this really cool idea, and we want to make a satellite that measures, weather patterns and all these different things. And so here's what we want to do, and they get money for it. And so they say, engineers, design us this satellite that can do these things. And so the engineers go and they say, okay, well, we can do this, this, and this, and it's going to cost you all this money. And the scientists say, no, we don't have that kind of money. and we don't have that kind of time. So it goes, it's an iterative process, and so the scientists say, okay, well, we'll change the parameters a little bit, we can give here, take there. And it's a circle, and so this happens throughout the whole life of the program, not just the beginning. Even later stages, right before launch, they're always giving and taking, and saying, maybe we should change these, the software a little bit here, or, test it a little bit more to make sure that we're going to be okay. So here's kind of an overview of the presentation today. We're going to talk about NPP. There's two main parts of a satellite. One being the bus, and the other being the payload. And it's important to know the distinction because it'll help us understand what we're talking about with NPP. So the bus is the structure of the satellite that holds all the electronics, power systems, guidance, propulsion, basically everything that makes the satellite go. It has all of the guts and the brains. The payload is the instrument. It's what does the measuring, the studying, the scientific research. And so for an optical satellite, it could be a camera that takes pictures. But in the case of NPP, there's 5 instruments. And they all do something very cool and very unique. We have, and I'll go through them later. I'm also going to talk about the environmental testing. So when we build a satellite, we have to make sure it's going to survive in the harsh environment of space. Also, we have to make sure that it's going to survive launch. Because when you launch on a rocket, there's a lot of vibrations and noises and all these things, and we don't want the satellite to break or have something go wrong when it's going up on the rocket. So we do a lot of testing ahead of time to make sure that we're going to be okay. Now I have a cool video that shows our launch of NPP that happened back in October. So this is a picture of, this is not NPP. If you've seen the model up here, seen pictures, you know it's not NPP because the solar arrays look very different. This is actually IceSat, which Ball also built. The purpose of it was to measure the elevations of Earth's ice sheets. And the reason we picked this picture is because it's very clear, it's obvious that this is the bus. And the instrument over here, that's the payload. And so this sensor does the science, and then the bus does everything else. It gathers power from the sun, it has communications back down to Earth, it has GPS sensors to tell it where it is, star trackers, which I will talk about, very cool instrument, radiators to keep it cool, and many other things. So at Ball, we build both instruments and buses. For NPP, we built the bus and one of the 5 instruments. And then we also integrated all of the instruments onto the bus and did all the environmental testing in our house. And we do all of that in Boulder. So here's a picture of the NPP bus structure. And you can see it's quite large. That's a person standing there. This is very early on. This is just the structural panels and with some of the wiring being installed. For most of our satellites, weight is very important because when you're launching something into space, you want the heavier it is, the more fuel you need to use and the more expensive. And if you get too big, you're going to need a bigger rocket, and that's even more expensive. So weight is very critical. And so our structural panels are made of aluminum honeycomb. So what that is you know what a bee's honeycomb is, right? What the shape of a bee's honeycomb? Well, we make that out of a very thin aluminum foil type material, and then we sandwich it between 2 aluminum plates that are very thin. That allows it to be very light and also very strong. So we bolt the whole thing together, and I was going to start to say that we do a lot of testing at each stage, but I'll talk about that more in the testing part of it.
So how much?
Yeah, go ahead.
How much does it weigh?
I'm not sure on the bus, just the structure itself. The full, with all of the components integrated, but not the instruments. The bus is about 2,000 kilograms, which is about 400 pounds. So that's for NPP. And that's one of our family of buses is in that range. And they're all similar, and so it's nice that we have a product that we can tailor to different programs, but it's still the kind of the basic design. And that's important in space, the space industry, because they like heritage. If something's worked in space before, let's do it again, because it's very risky to do new technologies in space, because if something goes wrong and it's way up there, you're not going to be able to do anything about it. NPP is unique in our family of buses because of the wedge shape, which is very obvious to see when you see pictures of it. And we'll talk about why it's shaped like a wedge a little later. And I forgot to mention, please, and I think we talked about it, please just interrupt me with questions if you have them ahead of time. Yeah.
Does the aluminum serve as a shielding as well for instrumentation at all? Or is
Um,
there something else in place for shielding?
So the instruments themselves usually have their own shielding built into their design. For the bus, obviously there's a lot of electronics on the buses as well, and so they all have their own shielding. We do electromagnetic interference testing to make sure that everything is playing well together. But we do grounding, electrical grounding to the bus. But shielding is kind of more built into each individual component of the structure.
How tall is the bus?
The bus, well, it's tall. If you stood it on end, it'd be taller than this room, for sure. We'll see a picture of it later of a person standing next to it when it's standing up, and it's about 3 people tall.
Good answer.
I don't.
Is that metric people?
Yes. I don't have the exact number.
Oddly enough, both metric and English.
Yes. We do not discriminate with people. Okay, so I mentioned that we started doing some wiring onto this. This is the flight unit, by the way, and that's a very important part is the cabling, because there's miles and miles of cables that connect all of the electronics boxes and the instruments and subsystems, everything. There's miles of it, and so we're able to use 3D modeling to design a lot of our components. But for cabling, it's much more difficult to do that. So we have to create a mock-up, which is an exact replica of the structure, and build all of the cables and route them all over the satellite so we know where they're going to go. It's also helpful to do that because we can get a good weight estimate of what our cables are going to weigh, and also center of gravity of all of our cabling, because our center of gravity is very important. So this is a picture of some technicians here putting together some of our cabling.
So is that USB 2 or?
No. I don't think that's a space qualifier connector there.
I noticed they're all dressed up. Is there a reason for that?
Yes, and so they're working in a clean environment, and I have a slide coming up, and I'll talk more about that. Working in our clean rooms and being all dressed up. Yeah.
Jason, could you speak up just a little bit?
Yeah, sure.
A couple people doing this.
Okay. Yeah, no problem. Okay, so leading to your question, that's the next slide. So here's the picture of one of our clean rooms. We have many at Ball, and you can see in the background here, let me get my pointer, that's the flight unit you just saw. And down here is our mock-up that we use to lay out all those wire harnesses. And you can see the tables of all the wiring there. And so this whole room, the clean room, is exactly what it says it is. It's a very, very clean room with these giant filters that keep the air very, very clean and the particles very, in a room like this, there's millions and billions of particles, and they range in sizes from very, very little to, hairs and things like that. This I'm not sure about this clean room, but our clean rooms are able to reduce those particles down to very, very tiny ones and a very low count. That's important when we build satellites because if any contaminants get in any of the instruments or into the electronics, there's a very high potential of that causing failure. And the risk is so high of having a failure on a satellite that you have to keep everything in a clean environment. We also worry about residues in addition to particles. So everyone always wears gloves. So you don't want, especially at Ball, we work with optics a lot. And if you were to get any residue on a mirror or lens, it would really destroy the capability of that. So a majority of our work is done in these clean rooms during integration and even during testing. We have different level clean rooms. We have some that, this one you can see they're just wearing gowns and some hairnets. We have very clean clean rooms where you are covered from head to toe and the only thing showing is your eyeballs. And that's for more critical components when they're being built. And while it looks like fun, and it is, if you're working there every day, it gets pretty hot and sticky, and you have to go through this long process of putting everything on, working, going out, taking everything off. So it is very tedious, but like I said, it's awesome. So here we're starting to get more components on our satellite bus here. The big box you see there is a battery. On NPP, there's 2 large batteries. The other one would go, this hole, there's actually an access panel that goes there, and the other battery goes on top of that. But you can see in this picture that there's a lot of stuff crammed onto this satellite bus. Space is very, very valuable, like I was saying with weight, because when you get more weight, you have more fuel and a bigger rocket. The same thing with size. If you get to be too big, you have to go to a bigger rocket, and that's much more expensive. So we try to keep everything tightly compact and small, and also lightweight.
What kind of battery?
It's a nickel hydrogen battery, and I'm not sure. I didn't mention this, but it's a good time to. Right now, we're working on the successor to MPP, and it's called JPSS, and it's the next generation of this type of weather satellite. And it's almost an exact replica if you look at it. It looks very similar, but there's some very key updates. And one of them is the batteries. We're going to the next generation of batteries, and they're lithium ion. So they're much smaller, much more efficient, and so that's a pretty big improvement. But I'll talk more about JPSS later.
Hey, Jason?
Yeah.
What's our time frame here? So you just launched this last fall?
In October.
So how far back is this picture? So like 1 year ago or 5 years ago? Or?
This picture was probably taken in about 2004-ish, long time ago. We built the bus on schedule, had everything ready to go, and then when we waited for the instruments to arrive, other companies were building the instruments, and they were shipping them to us to integrate them. Those schedules were very, very long and got backed up. So we ended up waiting a long time for those instruments to arrive. We didn't waste that time. We did a lot of testing, extra testing and extra analysis to make sure that we were good to go as soon as those came in. And it was really well done by our company because as soon as those instruments came in, we rocked it, and we had everything integrated in a very, very good schedule and supported launch on time. And for a satellite like this, where we have 5 different instruments all being integrated, and they're all built by different companies, it was definitely a circus of coordinating with all these different people coming in from different companies, and all trying to put their instruments on this one satellite, and they all had to play nicely together. So it was definitely a very, very cool thing to see.
So they ship those FedEx to you then?
Yeah. Priority mail. Yeah.
Priority mail. If it fits, it ships?
Yeah. one low flat rate. Actually, I do have some slides of NPP when we shipped it from Boulder out to the launch site in Vandenberg Air Force Base. So, there's some cool pictures of that. So, next slide. So this is one of the components on our bus, and these are really cool. They're called Star Trackers, and we build these at Ball. It's one of our components that we do very well at. And what these guys are is they're basically telescopes or cameras that look out at the stars. And just like when sailors were crossing the ocean looking at the stars to guide them, that's exactly what these guys do. They look at the stars and they know the positions of the stars, and they take in that information. They're able to tell us exactly where the satellite is and which way it's pointing. And it's very, very accurate. You see that there's 2 of them there. When we build satellite and put components on it, we like to put 2 of everything, or at least have redundant systems in case something goes wrong. We have a backup. Also, having 2, if they're both functioning, makes it more accurate.
Don't you have to have both of them for triangulation? How does it know where it is if it just uses one of them?
Well, we have other, yeah, that's a good question.
What was the question again?
The question is, don't you need both of them for triangulation?
Usually there's horizon sensors as well.
Yeah, there's
sun sensors.
we have multiple sensors. We have GPS antennas on there too. So, but that doesn't really answer the question. I'm not sure. I've always seen them in pairs. John, do you know?
GPS tells you where you are in the orbit, and by seeing a multitude of stars, it tells you which way you're pointing. So you only need one, but when you have 2, you get better accuracy on your pointing.
There you go. John is a comrade that works at Ball, so he's going to be piping in, and I don't know the answer to the question. So.
Kind of left you hanging there for a little bit.
Yeah, I know. I thought you'd speak up a little quicker than that there, John. So the next picture shows us our propulsion module. So that's this silver tank here, and so that holds all of our liquid propellant, and it fits right up into that little cavity there. You can't see it, but there's an entire deck below that tank, and connected to the bottom of that deck are the thrusters that fire when we're on orbit to give us orbit adjustments. We also, the NPP also has design for controlled re-entry. So at the end of the mission, they'll fire those bad boys up and send it on a predetermined path into the ocean.
What's the propellant? What's the fuel?
I believe it's hydrazine. Yes, hydrazine, which is very not friendly. It's very can be very poisonous to humans and toxic, and so they don't load that. They never load it with the fuel until right before launch, and it's a very big ordeal. People in suits from head to toe and breathing masks, and they look like astronauts with their suits on, just filling the propellant into the tank because it's a very hazardous operation. So here's a picture of the overall satellite structure, and you can see our solar array in this picture, you can see it's supported on these little tripods with wheels. Those actually aren't wheels, it's like an air hockey table. So the reason that we did that is because we're testing the release mechanism. So we call this test a pop and catch. So we'll stow the solar array, and then on the 4 points where it's connected to the satellite, there's what we call frange bolts. And these are bolts, it's a single bolt that holds on the solar array at each point, and when you fire them, a sharp, almost like a knife, shoots into the side of the bolt and it breaks it. It's a very special bolt, so it knows that it's going to break when it gets hit by this thing. And so that shatters the bolt, cuts it into 2 pieces, and that releases the solar array. And there's built-in springs in the hinges, so it wants to go out, it just can't until you break those bolts. So as soon as you break those bolts, it wants to open up. And so in this test, we're testing that it will open up, but obviously not all the way. But the next slide, yeah. Yes. How do they build the solar arrays? Well, it's very similar to the way they build solar panels here that we use here down on Earth. Like I was telling about the structure, with the honeycomb making it very lightweight, these panels are made of this same type of material, honeycomb, to make them very strong. And then they put the solar cells on there to absorb the sunlight. And when they absorb the sunlight, they're able to turn that sunlight into electricity. And that's what helps power the satellite. Because we put batteries on it, but batteries don't last forever. When we're up in space, we use the solar panels to gather the energy from the sun and turn it into power so we can power the satellite. You can see that we're still in the clean room. We have a guy there in a full, I think this is a very a higher level clean room than the previous picture, because you can see he's fully head to toe. You also see that there's a lot of this gold kind of foil, and that's what we call MLI, which stands for multi-layer insulation. And it's a thermal blanket. So one of the extreme environments in space is the extreme cold and the extreme heat, whether you're facing the sun or not. And these thermal blankets allow us to control that environment. And we put heaters in there to warm up the things that we don't want to get too cold, and we put radiators that radiate the heat for things like electronics that we don't want to get too hot. And that balance of thermal environment is much easier to do when you cover everything in this thermal blankets, because it makes it more easy to design to. So like these guys that are not covered in it, those are thermal fins. So those are radiators. Those are meant to radiate heat from the spacecraft. And the area of those is a controlled size so that we have a controlled flux of heat in and out of the spacecraft.
How much electricity do the panels generate to run it?
I do not know the answer to that question. So the question is, how much do the solar panels generate for power?
The short answer would be enough to run the instruments on the spacecraft. For an exact number, don't have that number.
Enough to keep the batteries charged.
Yes. And that's why there's different sized solar panels for every spacecraft. The size is determined on the power needs of the payload.
But the solar panels are just dedicated to charging the battery, right? Because everything would run off the battery.
I don't know if is that true? Yes. That's true.
Most satellites have one solar panel, or
So the question is, do most satellites have one solar panel, or do they most have two? Well, it depends on how you define solar panel. NPP has 3 panels that we call the solar array. And so they fold up like a book. It's a trifold, and so the 3 panels deploy and become one array. And every satellite's different. Some satellites, like the IceSat picture we showed earlier, it actually had 2 sets of 3 panels that folded down the side. So there's 3 panels over here and 3 over here. And so the answer is no. It's whatever it needs to be. So we can design satellites with solar panels that are there's 6 on each side if we need that much to look at the sun.
So it's not necessary for them to be symmetrical or balanced to keep going, right?
No, that's correct. It's easier to design a balanced spacecraft if they're on both sides. In the case of NPP, it flies in a what we call, not what we call, it flies in a sun-synchronous polar orbit, which means it flies around the North Pole and the South Pole, and the sun is always on the same side. And so we put all the solar arrays on one side, so they're always pointing towards the sun, and they'll rotate to follow the sun as it goes around the Earth. We call our jargon when we're talking about the spacecraft is that we call this the sun side, and the other side the cold side, because it never sees the sun. So if you have a chance to come see the model, on the opposite side of the solar arrays are all of our radiators that radiate the heat out into the cold space. And that's also where the bigger instruments are all shifted to that side so that we can mount the instruments directly to these radiators because they generate a lot of heat. And so the heat pours right into these radiators and it goes right out into space. Another question?
Thanks for coming, guys.
What's that? Sorry? Yes. Yep. Good question.
What was the question?
So the question was, does it need more panels because it needs more power? And yes. If you needed more power than this, we would have maybe 4. If it didn't need that much power, maybe we'd take one off and only put 2 on there. But this was just right. This is what we needed to power.
Do we use the same technology here to power buildings, or are they special?
Well, so solar, general answer to your question is that this is a very developing technology. As you probably know, there's solar cell technology is constantly changing. In space, solar panels are much, much more efficient because we don't have the atmosphere blocking the sun's intensity. So I'm not sure what the numbers are, but I think it's in the 90s of percent efficiency for a solar cell in space, as opposed to, I think they're working on technologies now that like 20,
They're working on 12 now.
12% efficient. Yeah, so you get a lot more bang for your buck on these guys. But it's essentially the same idea. So this picture, this is kind of the same idea as the last one, where we were testing the deployment. But this is a full deployment test. And this was a very cool test to do because these panels are so big and so long. And so it was the same idea where we have these air bearings at the feet of these guys, and this is a giant flat surface, these white panels, and so these air bearings right on it, just like a hockey table, real smooth. So we had to simulate zero gravity environment, and because if there was any resistance at all, they wouldn't deploy, and then our customer would say, "Well, they don't deploy. What are you doing wrong?" And if it was, say, sloped downward at all, they would kind of be helped along. So we had the biggest challenge to this test was making sure this, and we called it the dance floor, make this dance floor very, very, very flat. And that took a lot of time and effort. But it worked, and the arrays deployed very nicely, very smoothly. so that's kind of the bus side of NPP. Now I'll talk about payload, which is, payload means the 5 instruments that ride on NPP. And these are the instruments that do all the science. They measure weather and climate change. And so, what do you think the difference between weather and climate is? Any ideas? No? That's fine. So climate is over a much longer time period. If you want to check the weather, you go to your 3-day forecast and say, is it going to rain on Sunday? I hope it doesn't. No. But maybe you hope it does. Climate is the study of weather patterns over decades. And the climate studies help us to learn about global warming and things like that. And so these instruments are very helpful in determining both. So each one has its own kind of specialty, but they all work together to give us lots of data from both of those studies. Another question? Sure. So you want to, your question is what more about weather? Yes, they each have a different job, and I'll talk about them, each one of them individually. But yes, they each have a different job, and they each give us new information that lets us understand, you know, our Earth better. Everything from temperatures of our oceans and temperatures of the land. They measure our atmosphere. They measure clouds. They measure weather patterns around the Earth, storms. When there's big storms, they'll measure how intense those storms are, and they make really cool pictures too. We'll see a cool picture.
When they talk about the Doppler 3 or something like that on the weather station, do they use satellites like this, or is that something on Earth that's on the mountaintop or somewhere analyzing? Do you have any idea?
I
don't think you'd have the power.
Yeah.
Radar uses a ton of power.
Doppler is a radar system.
It's a radar system. Do you know where the source is?
Well, you know, they're all over the place. I mean, they're sometimes it's TV stations employ what they've got, and you know, so they're in a variety of places. National Weather Service has one going on, but they're not necessarily satellite related. I mean, they probably are. In a lot of those systems are using a composite part of it, but I don't know any of the details of that really.
The Doppler radar system that you see on TV and websites is ground-based in airports and between cities and like that.
Why 5 instruments, not 6 or 7?
That's a good question. We used to have 4, and series got added on at the last, well, not at the last minute, but very late in the program. And, you know, there's a lot of politics that go into that. And if there's not room for an instrument on this one, maybe there's room on another satellite that'll go up on. But a lot of that is determined pretty early on in the program, and they, decide what instruments they want to fly on this particular satellite, and then we can design the bus to accommodate those instruments. Another question?
To go back to the weather data,
Mm-hmm.
don't they also use like weather balloons where they can attach instruments into the atmosphere to see their wind range?
Yes, absolutely, and that's used a lot. And this is, it's all kind of the same science. They're all these things are trying to do the same thing, and this is just doing it from a different point of view. This is doing it from space, looking down to measure, all these things that we're trying to learn about weather, because weather is not an easy thing to understand. It's always changing, and so we're trying to keep up with our instruments, trying to learn more all the time. So I don't want to gloss over these, but I'm going to tell you a little bit about each one. But this isn't my area of expertise. But I can tell you what they do. So this is beaters, and this is the biggest instrument that we have, and it sits on top of the satellite. It's pretty big. It weighs about 600 pounds, 650 pounds, and it's by far the most technologically advanced of the 5 instruments. So this was a very big part of the payload. What it does is it does a lot of different things, and it's a brand new instrument that's never been built before, but it relies on a lot of technologies that have been already designed. So we have it measures clouds, it measures temperatures of the Earth's oceans and land. Let's see what else. It produces visual imagery, and we'll see a really cool picture of the Earth taken by viewers. And it does so many more things. I can't even cover them all because I don't understand the science, but it does a lot of things. Yes.
Jason, what are they doing in that picture? And how can that engineer or technician be standing right under this thing that weighs like 600?
That's a great question. Yeah, I don't think it's quite underneath it either. We try not to get directly underneath, but it's what they're doing here is they're installing it. They're installing the instrument onto the spacecraft. It's going to go right there, and you can see there's guys already ready to go. And this is a very long process because it's very delicate. These things are big and heavy, but they're also very delicate and very, very sensitive to vibrations and things like that. So the integration part of all these things is thought about way in advance. And so they designed in some hoists in the instrument and put them in spots where they know that they can lift that thing in those spots and not drop it, which is good. And so this thing weighs so much, you have to use a giant crane to lift that guy up and move it into position and slowly lower it down onto the spacecraft. And since this is such an important part, there's lots of eyes watching while this is going on. Lots of black tie people watching, making sure that this is going off without a hitch. And there's lots of planning that goes into it before it even happens. Especially when you wait 6 years for it to happen.
And that's in a larger clean room than what was said before.
Yeah, the program kind of moved through clean rooms. At the bus level, we were in a small annex clean room where we could work to get all the components on. And this picture is actually our newest clean room. It was just built 2 or 3 years ago. 3 years ago. And so it's a little bit bigger, yes. And you can see our nice big American flag on the wall. But we're in the process right now of building new clean rooms. We're still expanding and making more room for what's to come next, which is hopefully more of these. So this is another instrument, and this guy is called Chris. Well, actually, did it say up there? Yeah, so that's what VIRS stands for, if you're interested. It's a lot of, visible infrared, those are the wavelengths it looks at. Imager radiometer, that's what it does. So Chris sounds like a cool name, and it stands for Cross-Track Infrared Sounder. So this is So this instrument, along with the next one I'll show, ATMS, they kind of work together, and because they both do the same science. Chris and ATMS together, the main goal is to kind of look at moisture and pressure profiles in the atmosphere, and especially focus on storm systems when there's hurricanes or tornadoes, and they're really good at measuring the profiles of those as they're happening, and that's going to give us more information about storm development and things like that. They also measure the atmospheric temperature as well. So this is ATMS. This is the other to the pair that I was just talking about, advanced technology, microwave sound. And so they work together because this guy is able to kind of see through the clouds and uses its sensors to measure humidity and things like that. So this is ATMS. This is the one I just showed you, and then over here is OMS, which is an ozone mapping and profiler sensor, and it measures our ozone layer. It's actually comprised of two separate small instruments, and one looks straight down at Earth and measures the ozone from overhead, and the other one looks at an angle, so it can measure the vertical profile of the ozone layer as well. It's a brand new instrument. We obviously have other ozone instruments out in space that have been taking data for a long time. This is going to extend that and make it more accurate and give us a better idea of what our ozone layer looks like. It's going to measure the hole in the ozone layer as well. That's always a big, interesting topic for people because it's very important.
So is that I'm not sure why is that found in the hole in the ozone layer?
This instrument did not find it, no. But remember I was talking about Suomi Werner Suomi, who's named for this? He helped build some of the instruments that did find that ozone hole that are flying in space.
Can you speak up a little bit, Jason?
Yes. Thank you.
Jason, who receives all this data? And what's the main organization that this was built for?
It's all public data. And NASA Goddard, I believe, is the one who manages all of it. And it's for scientific use for any scientist that wants to look at the data and do research on it. Obviously, there's a lot of scientists that were in on the development of this that are very, very interested in it. But yeah, it's public information. And if you go to the NASA Goddard website, you can pull up data from any of these instruments at any time.
Is it constantly streamed?
Yes. Yes. It dumps data to a station in Norway, but it has a recorder on board that's constantly recording all the data. But all the instruments are operating 24/7. And OMS was built by Ball as well, one of the 5 instruments that was built. So here's Ceres, and this is one that came in later in the program. This is the picture of them, them installing it, and this guy measures the radiant energy of the Earth. So the sun hits the Earth with energy. Some of it bounces off, some of it gets absorbed. And the Earth also produces energy that leaves into space. And so this measures all of those things and kind of maps our budget of energy, how much is going out, how much is coming in. And that helps us with our global warming research. And a big factor in how much energy is absorbed or reflected is clouds, because clouds reflect the sun's rays, so it measures clouds as well. Over here in this picture, you can see this little dome that they're putting over the top. That doesn't fly with the satellite. That's just for when we're on the ground. It provides a nitrogen purge, so it's a very inert environment to protect their sensors. And as far as that goes, when we're on the launch vehicle, inside the fairing on top of the rocket, everything is purged with nitrogen to be very inert because it provides a very stable environment. So here's a picture of everything integrated, all 5 instruments. You can see, I mean, this is a pretty late in the program before we're going to deliver because it's got all of the thermal blankets installed. You can see that we're installed here on our what we call an MTAP, which stands for mechanical 3-axis positioner, which is allows us to rotate the satellite in all different directions. We can tip it, tilt it, and rotate it, so we can work on it very easily. You can see this guy under here. He's very thankful that we can do that, so he can reach up there and do what he needs to do. So this is a cool video that we've got, and it's going to be a fast motion video of the instruments being installed onto the spacecraft. There's 18 minutes. OMS is the instrument that Ball designed. Here comes the big one, Beers. Chris. Here we're lowering it into our large vacuum chamber, which I'll talk about in a minute. Installing the solar panels. And here's a little preview of the launch.
5, 4, 3, 2, main engine start, 1, 0, and lift off of the Delta II with the NPP satellite, blazing the way in new technology for climate research and weather forecasting.
So you may have seen towards the end there, the solar panel had some, like a picture on it with some words. That was just a cover that was helps protect the solar cells before we launch. So that obviously comes off before we launch it. But if we're going to put a cover on there anyway, we might as well put our logo on it and make it cool.
I think we ought to let the audience work a little bit here. So does anybody know why the satellite was launched from Vandenberg?
That's in California, right?
It's in California, correct.
Is there less?
A young man over here had his hand up.
So if it failed, it would destroy wherever it was built?
That's true, but that's also why we launched from Florida, though, too.
So it has to do with the weather?
That's part of the reason, but there's another more fundamental reason why it launches from Vandenberg as opposed to from Florida.
So you get in the orbit?
Correct.
What was the answer?
The answer was for polar orbit. It launches towards the south, whereas when we launch from Florida, it launches towards the east. For normal east-west orbits and versus polar orbits.
Yeah.
In regards to the polar orbits, when do you actually change from north to south, south to north? Like around the equinoxes? Is it when you change the orbits?
Not sure I understand the question. In a polar orbit,
It's always kind of, it's when it passes the pole, right? And
Well, so it orbits about the Earth such that it goes over the top of the North Pole and then around underneath the South Pole. And then it moves over, the orbit is such that it's slowly moving around the Earth, and it orbits the Earth 14 times a day. And so that allows it to see the entire surface of the Earth twice in a 24-hour period. Half of that will be in the nighttime, and half will be in the daytime.
Can you see it at night, like Sputnik?
Believe you probably can. I haven't looked, but I don't know what, I don't see it.
Yeah, you probably could at certain times. I mean, you can see certain, polar orbiting satellites at different times of day. You have to catch it at the right time of day, though. In fact, I could look that up for you if you want.
What's the total project cost?
Oh, yeah.
Can somebody help me out with that question?
Millions of $1 billion.
What's that?
Including the launch and the ground station, it's over $1 billion.
It's over $1 billion.
How much do you pay for insurance?
Not as much as it costs to build a satellite.
So that's a 5-year life.
Yes. 5-year mission life, yes. And groundbreaking info is that the rocket, the launch into orbit was, we have a certain amount of the propellant that we have to adjust our orbit once it's launched, and then for orbit adjustments throughout the life, and then obviously some saved for deorbit. Well, our entry into orbit was so accurate that they didn't have to use hardly any propellant at all. So we have enough propellant, assuming everything else lasts longer, to last us several more years.
But part of that length of time, though, is because the project was delayed, right? The actual build time was about 3 years of that time, right?
So when you talk about mission life, you're talking about from launch to end of mission when they deorbit. But the time frame for the project, has been much, much longer. It took 8, 9 years.
But a lot of that was delayed, though, right? It wasn't all, you weren't building that entire time.
No, not at all. Yeah.
How much did the total project weigh?
The whole thing? I don't know the exact numbers, but it weighs well over 5,000 pounds. So it's pretty big, pretty heavy. So talk about our environmental testing real quick. Like I said before, we have to test for the extremes of space, but also the extreme environment in a rocket. You can imagine being on top of a rocket that's launching. It's going to shake a lot. And these instruments are very sensitive. And so we have to make sure that we run these tests to make sure that everything is going to be okay, that we're not going to have something break during launch. Or in the extreme vacuum of space, we have to make sure we vent all of our paths so any air trapped inside can get out so you don't burst the bubble. So one of the things we do is a vibration test. And so we have this vibration cable we install the satellite on, and it literally shakes it. And we do several different types of vibration testing. We do testing that simulates the really extreme acceleration as you're launching, the G-force of a constant acceleration. We can simulate that on a vibration table. We can simulate the launch loads that translate the spacecraft back and forth, that really rattle it. And we do that at a lot of different levels throughout the program. We'll do a vibe test of just the structure, and we'll do a vibe test with some of the components on it. And then obviously the full up model, or full up satellite. We'll vibe test that as well. And assuming nothing breaks, you're good to go. We also do electromagnetic interference testing. And so we have this large EMI chamber. Like I said before, all these electronics are operating in very close distances to each other. We want to make sure that none of them interfere. They're all giving off these minimal electromagnetic signals, and so we don't want them interfering with other instruments or boxes. So we have to test, make sure they play nicely together. So this is another cool test. This is to simulate the environment in space. We have a very large vacuum chamber, and you're seeing just the very top of it. It's about 2 or 3 stories tall, and there's a big lid on top that we lift off, and we can lower in these satellites. So this is NPP getting lowered down into our large vacuum chamber. So once we get it in there, they'll pull out all the air and make it a vacuum, and then they'll make it really, really cold to simulate space. And our tests in these chambers can last for months to simulate, to go through, operate all of the payload instruments and make sure that they operate correctly in this environment.
How deep a vacuum do you have to hold us in some space? Is there a limit, I guess? You have to hit sort of micron level or anything? I mean, what's acceptable to shoot in space?
I don't know if we reach space values as far as pressure. Pretty close if we don't.
Yeah, it's pretty close. I mean, even space itself isn't a complete vacuum.
Right. And you can't get a perfect vacuum in a chamber, you know, like this. But we get pretty close. Close enough that they're able to accept the testing of the instruments, obviously.
They might be interested to know the name of the chamber.
What's that?
They might be interested to know the name of the chamber.
So this is our largest chamber, and it's fondly called Brutus. So we all of our chambers have a name to them. We have Rambo and others, but Brutus is probably our favorite. Hopefully, in our new expansion, we'll be getting a bigger one in the future. So here's a picture of it getting lowered in. You kind of also saw it in the video as well. And so they'll bring this down. All this equipment inside, this is all test equipment, targets to simulate thermal environments and environments that the instruments can actually measure and test the accuracy of their sensors. And this is one of the largest, most complex tests we've ever done at Ball, because NPP is so complex with 5 different instruments testing all at the same time.
Do you test for space junk?
The question was, do we test for space junk? And no, that's obviously a problem. There's a lot of space junk up there, and you don't want something hitting your satellite when it's up there.
If we do that, then we gotta fix it, and that just takes longer.
Yeah. Yeah. It would be fun to shoot space junk at it to see if it worked, but I don't think the big wigs would like that.
The guys at NASA, they get kind of upset when you do
Yeah.
that.
So here's a picture. This was earlier on in the program, but it's a picture when we did a thermal vacuum test at just the bus level. Obviously, you can see none of the instruments are on there yet. But these are some of our technicians taking a glamour photo while it was installed in the vacuum chamber.
Dave in that picture?
Dave,
Yeah.
I don't think so.
Why
I
would
wanted to
the-
be in all.
Why would the scientists not be wearing their face masks?
So it's a good question.
What was the question again?
Why aren't the scientists, or why aren't these guys wearing their face masks? Mostly it's for the picture. They're supposed to be wearing them. But when the photographer says smile, if you have a face mask on, you're not going to see it.
They were all disciplined soon after.
But we
Is that a 30-second window to take that picture then? Or?
yes. It's like the 3-second rule. As long as it's not for very long, you're okay. So once we're done with all of our environmental testing, and one thing we don't have a picture of that we also test for is acoustic environment, which when you're launching on a rocket, there's a lot of sound waves that are coming from these large engines that are just that are firing to launch into orbit. And so, you know, if you're at a rock concert and you can feel that bass in your chest, it's very similar to that, but on a much bigger scale. And so the acoustic vibrations are very important to test for as well. And we don't have a picture, but we do that as well. And we literally set up speakers, large concert speakers, the height of the spacecraft all the way around it, and blast sound waves to test for the acoustic
How
environment.
many decibels?
You know,
Well over 100.
140.
Is it Pink Floyd or?
There's jokes that after the test they put in their favorite bands and have a party.
125 or roughly is jet engine noise. Somewhere in there.
180 is the loudest concert. I like
Yeah, and they definitely do the testing at night when nobody's around for safety reasons.
Well, the neighbors complain anyway.
Yeah.
Call the police.
So here's a picture. We packed it up in this. This is a very controlled environment inside this box that we put the satellite in, and it's cool. So I was talking about how we design for vibration on launch. We have vibration when we just drive it from Boulder out to California, so that's important as well. And so there's vibration dampers and things like that inside here. Yeah.
What happens if the truck rolls?
There's insurance for that as well. There's a convoy that goes. Just like you see when the oversized loads trucks come by, you have a car in front, a car in back with flashing lights. Same thing here. It's very expensive satellite in there, so they take all the precautions to make sure it's a safe transport.
So how fast do you drive down the highway?
I would say they stay under the speed limit. Yeah, I don't know.
I mean, do they have to drive slower?
That's a good question. Do you know, John?
I can drive to the lunch site in about 20 hours in my car, and I think this took almost 40 hours to get there. A little faster than this.
Is that Federal Express or UPS?
So we have a video of we saw a video of the launch before, but this is kind of a more. Oh, sorry, that's describing our pack to launch. So, so here's another picture. This is arriving at the launch site intact. Clicker's not working. There we go. So here's a picture. This is goes to show you what the space is like inside one of those fairings. The fairing is the top of the rocket that the satellite sits in, and it's a controlled environment, and it sits on top of all the propellant and rocket engines and those things. So this is showing inside the shell of that fairing, and this is what we mount to. And you can see how tight it is in there. And this is a top view. If you were to look down into that fairing from the top, you can see how close to the edges we are. It's a very tight fit, and it makes it even more important for that vibration testing that we're not going to deflect far enough to hit a wall. But also for the design challenge, way back at the beginning stages, when they were determining which rocket should we choose to launch NPP on, that was done in parallel with the design of the satellite. And so I was talking about the wedge design, and that was a solution to the problem. How do we fit this into a round tube fairing? Well, the wedge design lets us put veers, which is very large, on top, and these little ones like ATMS and OMPS at the bottom, and be able to fit into that volume. It's also why the solar arrays are folded up and secured to the side, so we can fit everything inside of there.
And on this picture, which is the hot side and which is the cold side?
So we're looking at the cold side. So these are the radiators that I was talking about that emit all of the heat. So this ATMS mounts directly to this radiator to get its heat out. This is a radiator for veers. And so the hot side, or the sun side, is the solar array side. So in this picture, it would be the opposite side. In this picture, this is the sun side, and over here is the cold side. So all the instruments point towards Earth, so Earth would be that way. And then this is pointing towards space, which is why our star trackers are back here, pointing towards the stars. So here's an actual picture of it in the fairing before we launched. As you can see, it is quite a tight fit in there. We Ball, you know, when we support integration and testing, we also support all the way up, all the launch operations, all the way up until launch. Until it separates, we're involved in the process. And when I say when it separates, once it's in orbit, when it deploys away from the main rocket down here.
So is the satellite on the very top of the rocket?
Yes. So the question was, is the satellite on the very top? And here's a picture of that fairing that it's inside of, and they're hoisting it up, and they're going to put it all the way up on top of the rocket. I think so yes, the answer is yes, it's on the very, very top. The rest of the rocket is holding the engines and the fuel and all of those things to get it up. So the rocket that MVP was on, it has 2 stages. It has a main engine with liquid propellant and 9 solid boosters. 6 of those are lit on the ground at launch. And then in a certain amount of time into the launch, those 6 fall off, and then the other 3 light at that point, and that puts it further into orbit. And then the main stage cuts off, and then it starts a second. So then the main stage falls off, and then a second stage of main lights, and that puts it the rest of the way into orbit.
What happens to the stages that don't make it into outer space? Do they burn up coming back into the atmosphere, or do we go collect them on the ocean, or
I
do we just let them
believe
sit?
they have chutes. Don't they, John? Do the solids have parachutes? Do they collect those?
I don't think they collect those.
No.
Not on the Delta.
The only boosters I know that they were used on a regular basis, so it's all
Shuttle.
boosters from the shuttle.
Yeah.
Even the main tank, pretty much burns up. But it depends on how high it gets and everything else, what happens. But,
Another question?
any other questions?
Yeah.
How tall is the launch pad?
How tall is the rocket in the launch pad? Oh, good question. Any guesses?
21 stories high?
21 stories. Anybody else have a guess?
It's probably not right.
Yes.
20 stories?
20. Does anyone know the real answer?
Well, you're 19. Well, you're 19 stories.
That's probably about right. It's very tall. We'll see in the video. It'll show the entire rocket. Actually, let's just go ahead and play it right now.
Is the spacecraft in the controlled environment as it's being lifted over the top of the rocket?
Yes, all the way through launch. It's nitrogen purged.
8, 7, 6, 5,
And so some of the umbilicals that are connected
2, main
are
engine
purging
start.
it all the way up until it's separated.
0, and lift off from the Delta II with the NPP satellite, blazing the way in new technology for climate research and weather forecasting.
So it just hit supersonic speed. The speed of sound. See it brighter there, that's when they lit the 3 initial solids. And pretty soon you'll see the solid rockets fall off. There'll be 6 of them. There they go.
That's out over the ocean?
October. October 28th, I believe.
So we communicate with the other nationalities around the world so they know that we're not bombing them.
I believe so.
How did they videotape?
That's a good question. He asked, how do they videotape this? And I don't know the answer to that, but it's pretty cool.
Pretty sophisticated, can't tell.
Yeah. I tell you what, they weren't able to do this, until recently.
How fast did you say it's moving?
3,200 miles an hour.
I think that's what he said. Mach 10. 10 times the speed of sound.
It's gotta get to 16,000, doesn't it? Escape Earth orbit.
I'm not sure what orbital velocity is.
17,500.
There you go.
Data coming in through Senate is Pete. Santa Barbara.
So ultimately, how fast is it going around the planet? What did you say?
Approximately 17,500. That's escape velocity. Maintain stable orbit.
And do most satellites move at that speed?
Yeah.
Depending on their orbit height, yes.
Okay.
Yeah. If you go too fast, you're going to shoot up into space. If you go too slow, you're going to crash into Earth again. So you got to go at that right speed, so you're always falling over the edge of the Earth, and that's called the orbit velocity.
It's also dependent on the height of the orbit too. And the relative speed.
So the entire launch, all the way up until separation, lasts hours, and then eventually the fairing will separate. It's a clamshell, so it's two halves, and so they'll fall away, and then they'll eject NPP spacecraft off of its base, and then they'll deploy the solar arrays, and then that was in October, and it took several months of commissioning to ramp up every instrument. They have a lot of testing goes on before they can operate and take data, and that just completed about a month ago. Every instrument was fully operational and working great.
How high?
Whoever asked at the height of the launch pad, it's such important information, it's not even listed on the website.
It is 70 meters.
So what altitude is it?
So NPP is at about 560 miles, I believe. I don't remember here.
Do you have to register for a certain altitude? Just like, in flying, if you're flying west or east, you have to be at different altitudes so you don't hit one another?
Yeah, that's all. NASA tracks every satellite in space, whether it's meant to be there or not. There's a lot of space junk that's not
So you have
supposed to be
them
there.
at
And
different altitudes to keep from hitting one another?
the altitude is largely driven by the science. The instruments, determine what altitude you should be at. They probably fine tune it to make sure they're in a clear orbit. But there's a lot of space up there, so it's very difficult to run into something else. Yeah.
With that, that fuel they use for the rocket ships and the other things, are there people in the satellites?
There's no people beside
There's no people in this rocket or on this satellite. When the shuttle launches, people would go in the shuttle, and there's rockets that they use now to get up to the space station that have people capsules on top, and those are designed in a whole different realm. The safety requirements for those missions are much higher than the ones we use for satellites, because there's much higher risk when you have a person involved.
Is it?
So there was a question earlier about can you see the satellite as it goes overhead? There's a pass that's visible to the east somewhere around 1 o'clock this morning, but the problem is you have to be able to catch it so you're actually getting sunlight reflecting off of it. So I guess at that time of day, you're not going to get any sunlight off of it. And you have to look at it and figure out when you're going to get it at the right time of day that will get a little bit of sunlight off of it to be able to see it.
So we have one more quick video, and this is just, it's not a real video, it's an animation that was created that kind of shows the NPP instrument in orbit above the Earth. Oh. Yahoo! Yahoo!
You're fired.
So it's a good view of all the instruments pointing down at Earth. You can see Veers has opened up its doors here. And you can see the solar array deployed fully. So it's just a short little animation with our model.
Okay, great.
And this is very breaking news. You may have seen it. This is what they call the blue marble image. And this was taken by Veers just in the last month or so. It's actually a composite of a lot of images that it took much closer up. And then they stitched them all together to get a full view of the Earth. And it's a very high definition view of the world taken by Veers. And they had so much response from this image, NASA did, that they, a lot of positive response, but then a lot of people saying, well, what about the other side of the Earth? So they had to do another one showing the other side for all the people, you know,
Somebody's always left out.
in the other countries, because they wanted to see where they live.
Jason, what was the name of that image again?
I'm sorry?
What was the name of that image again?
The blue marble.
Blue marble, and I looked at it, if you haven't seen that, take a look on your computer screen, because you can zoom in, it's such high resolution, it's absolutely beautiful. It really is spectacular.
It's amazing. And it's only, this is only a tiny, tiny amount of what those instruments do, is take pretty pictures. They do so much more than that.
So Veers can't take pictures of other planets,
So the question was, can Veers take pictures of other planets? But no, just Earth. So all of these instruments are pointing right at Earth, and they're very close to Earth. They don't look out at the other planets. So no.
But another ball satellite does.
Yes, we have lots of satellites out there and lots of look at other planets. In fact, Kepler is another popular satellite that Ball built, and Kepler is trying to discover Earth-sized planets out around other stars in our solar system. So it's looking at a group of stars out in space, and it's measuring the intensity of the light coming from that star, and it's measuring little dark shadows that travel across the face of that star. And it's so precise that they're able to determine from that little dot that goes across the face of that star whether it's how big of a planet it is that's orbiting that star. And they've found hundreds and hundreds of planets just in the last few years from the Kepler spacecraft that Ball helped build. So it's pretty cool stuff. And so that's the final picture. I believe that's my last slide. So is there any other questions? Anything?
What about JPSS?
Yes. So JPSS, actually that is a picture of JPSS. Sorry. It's so similar to NPP, I thought it was NPP. So this is our next generation weather satellite. It's very similar to NPP. It has all of the same instruments, Veers, CRIS, ATMS, OMPS, and Ceres. Something new you will see that's on JPSS is this antenna boom, and that's a new deployment feature that's going to improve our communications on this satellite. It's during launch, it's just like the solar arrays, it's stowed. It's bolted to the spacecraft. It kind of wraps around the side at a 90-degree angle. And then on launch, it'll deploy on both hinges. And then on the very end, the antenna is on a gimbal, so it can maneuver around to get accurate communication. So that's one of the improvement. I talked about the batteries improvement. There's lots of other hidden improvements, but those are the visual ones. Yeah.
Are they steering that satellite from Earth?
Question is, are they steering the satellite from Earth? Question, and the answer is yes. That's why we have all these antennas on here. They're transmitting data down to Earth. Everything from the science data from the instruments to which way the satellite's pointing, where it is. We call that attitude determination and control. And all that data is taken in, and we can transmit signals back to the satellite and can control some of our positioning mechanisms to get a nice, accurate pointing towards Earth.
Who asked the space jump question earlier? Somebody asked the space jump question. Do we check for space jump damage or anything during testing? Well, that would be one of the things they could possibly do is move it slightly out of the way of another object. That would be
Yes, and adjust the orbit in general. Did you have a follow-up to that? Another question?
It was, how do they steer it from Earth?
How do they steer it from Earth? Well, they take in the data and they decide, okay, we want to turn it a little bit this way. So they transmit a signal that's received by one of the antennas on the satellite, and there's computers on the satellite that are able to process that information. And we have things such as gyroscopes and other things that can kick in and move the satellite a little bit. So they're actually talking to the satellite through antennas.
So if they say like it needs to turn right or left or something, they transmit that to the satellite and then it turns right?
Yes, exactly.
It's got several motors on it.
Yeah.
So with the data that's collected over a 5-year period on climate change, how many years into the future are they going to try and predict what's going to happen climate-wise? I mean, how many years do you need in order to predict what's going to happen in the next 100 or 200 years? I mean, if that's what you're doing this for.
I don't know if you can extrapolate that.
So, well, we want to know about the climate, right? Because we're trying to predict what might happen in the future. So how many years do you need to predict out the years that you need?
The short answer to that is as many as possible.
Yeah.
Take data from many, many programs, many different satellites, and kind of build trends based on those. Even in the late 70s, when the first weather satellites came up, those are basically the first data points that we have from space observation for climate trends. So building on data that we've had over a long period of time is how scientists are able to determine those long-term climate trends. So the short answer is as many years as possible and many years into the future.
There's always going to be some degree of error in those models. I don't know that you could reasonably expect this mission by itself to be able to provide all that data.
And that's why we're building JPSS to continue that data. And so this is hopefully the first of many JPSS satellites. The idea is to build 2, 3, 4, 5, keep going with these.
Will this one last longer than 5 years with improved battery technology? Or?
John, you know what the mission life on JPSS is?
Most of the electronics are the same, so it's probably the
Probably 5
same.
years.
Probably 5 years. It's probably about the same.
Can I interrupt for a little bit?
Yeah,
It's been
absolutely.
going on for an hour and a half almost.
Oh, look at that.
Anybody that wants to
They've
go
been doing
look
it so
at
much.
through the telescope, there is some clear skies, so we can do that. Anybody else that wants to keep discussing things with Jason?
Any other questions?
Yeah, thank you very much.
Lots of questions.
Yeah.
Was it difficult or?
No, not at all. Very good questions.
Or are there other satellites?
John, you go upstairs.